Software Development. Chapter 6. Aims: to introduce different approaches for developing software systems, testing those systems, and ensuring software quality. Introduction. The past. When software systems were first developed in the mid-20th century, they were done so in a rather ad hoc manner, without any reference to a defined development process. It was soon realized that this undisciplined approach led to systems that were poorly constructed and difficult to manage and control. Some form of development process was required that could assist software developers in producing more structured code in a more manageable way. According to Nutt and Dawson, the advantages of structuring software development into a defined process model are that it divides a large problem down into easy-to-understand tasks at each stage. It sharpens focus. It supports planning and control, improves time estimates. It provides progress visibility. It provides structure. It leads to better coding and documentation. The same is true for student software development projects. By following a recognized process in the development of your software, you will reap benefits outlined, therefore introduces some common development approaches that you can use and perhaps adapt for your own project. 6.2 The Software Development Life Cycle or SDLC. Introduction. The SDLC represents a generic model for software development and consists of a number of stages. These stages, Figure 6.1, are requirements capture, design, build, test, and implement. All software developments follow this generic model in one way or another, and yours will do the same. Requirements capture represents all the activities that are performed to elicit the requirements from the user and the documents that are produced during this stage. Design represents the design of the software based on the requirements. Build is the coding or development of the software system. Test is the testing of this code, and implement is the eventual installation or acceptance of the software system in its target environment. This can also include evaluation of the system with respect to the user's initial requirements. In practice, there is often some overlap and iteration between these stages. For example, if you develop a prototype, you will be performing some requirements capture, some design, and some building work simultaneously. You will then perhaps return to the requirement stage to redefine these in light of feedback from the prototype and repeat the design and build these stages again. Build and test usually overlap significantly. By understanding how large commercial software systems are developed, it will help you in the development of software within your own project. The following section discusses in more detail each of the stages of generic SDLC. Requirements capture. Requirements capture is often the hardest stage of SDLC to perform well and subsequently get right. Numerous methods and techniques can be employed to capture a user's requirements for a system, and whole texts are devoted to this issue. The outcome from this stage of the process is a series of documents that clearly define what software system is required to do, but not how it should do it. That is the purpose of design. These documents should be produced in the following order. 1. Requirements definition. 2. Requirement specification. 3. Functional specification. You would probably not produce all these documents separately as part of your own project, but may be required to produce a single requirement report or system specification that encompasses the essence of each of these. Figure 6.2 shows the conventional process of requirements capture. We will discuss the time problem ovals later. Stages in ovals can theoretically ambiguously. Stages in clouds cannot be clearly specified and represent qualitative understanding or subjective documentation that contain ambiguities, contradictions, or unclear statements. In Figure 6.2, we begin on the left-hand side with a problem that needs resolving. While the user's understanding of this problem is subjective, they may not fully understand the problem or all its corresponding issues. The problem itself is, in reality, unambiguous. Unfortunately, the user is our only link to this problem. They are the experts in this area. As their understanding of the problem is not perfect, notice the user understanding cloud in Figure 6.2. We will be developing a system on incomplete or ambiguous knowledge. The analyst attempts with the user to define the problem and produce a preliminary definition of the user's requirements, what they require of the system. This stage of the process results in a requirements definition that is written in the user's terms, usually in natural language or English. Because this document is written with the user and is based on their incomplete understanding of the problem, it is likely to contain contradictions and ambiguity, and hence it is also represented by a cloud in Figure 6.2. It is also possible, even with a single user, that the requirements definition can contain conflicting requirements even at this stage. The analyst must then take this document and rewrite it ambiguously to produce a requirements specification. This is much more formal structured document that is not open to interpretation, hence the oval in Figure 6.2. It forms a basis for a contract between the client and software developers, and consequently it is important that it is properly and professionally produced. It states that the user is expecting the system to do. Having identified the requirements for the system with the requirement specification, it is now the job of the analyst to specify one system that will satisfy these requirements. Functional specification. This document usually contains an introduction, a rationale for the system, project objectives, functional requirements, and non-functional requirements. Functional requirements states what the system is required to do and the data and user interface requirements. Non-functional requirements refer to various constraints, standards, limitations, costs, delivery dates, configuration, language, resources, etc. Performance requirements, verification requirements that ensure conformance with the system specification, and validation criteria, which form a basis for system testing after the system has been written and tested. You should be clear in your own mind as to the difference between functional and non-functional requirements as fulfill these requirements when it is complete. The functional specification should be an ambiguous document that states exactly what the system will do. Having decided what the system is supposed to do during requirements capture, it is now the time to decide exactly how the system will achieve this. This is the purpose of design. Design works on a number of levels and a number of issues. For example, systems can be designed as a series of modules or objects that are gradually brought together to produce a fully working system. Design can include flowcharts and pseudocode that plan how certain functions within the program will operate. Object-oriented design techniques, for example, UML, can be used to build systems for a series of objects. Design can also encompass interface issues, human-computer interaction or HCI, screen layouts, navigation between screens, and storyboards. Design might include database design, for example, structuring data tables using normalization and techniques or entity relationship modeling. Build simply represents the coding and construction, bringing together the individual modules or objects of the software system. How this is achieved depends largely on the programming language used, the design methods used, and any coding standards and quality standards you might be following. 6.2.5 Test. This is the final testing of the system as it is brought together into a working whole. Implementation. The final stage of the SDLC is implementation. The requirements, the final handover of the system to the user. It can include acceptance, testing by the user. It will invariably involve training. It might involve a formal handover, the setting up of data files, implementing new work procedures, documentation, and so on. In this stage of the process, change management is particularly important. This can also include overcoming resistance to change and data migration issues, etc. Having introduced a generic model showing the broad stages through which all software systems develop, we will now look more closely at specific models you can use and adapt for your own project. The earliest model, build and fix. The build and fix or code and fix model represents this early approach to the development of software. It is not a formal model as such, but a representation of simple approach to hacking code together. As we saw earlier in the pioneering days of software development, there was no recognized process for developing software. Programmers merely attempted to grasp an understanding of the problem as best they could and cobbled together some code to address this problem. There is no formal requirements captured in the process and no formal design. Programmers would first write some code, run the code, and then correct any bugs in the software. In this case, there is no formal breakdown of the process into stages. The model merely iterates until the software becomes unworkable and is eventually retired and or replaced. Although the approach is still used today by many programmers working on small and personal systems, you should not be using it for your project. You should instead look to one of the more defined and recognized processes outlined in the following sections. Turner identified a number of issues with this model. After several fixes, the software becomes difficult to maintain as it becomes poorly structured. It often does not match the user's requirements, it is rejected or requires extensive redevelopment. It can be costly to maintain because of its poor structure and lack of definable output that can be tested. Um, that's all. Thanks. All. Thank you.